Hello everyone. Now time to deliver the lecture number 25 in the lecture series of thermodynamics, and the topic which is going to be discussed is entropy of an ideal gas, and finally some numerical problems on entropy will also be discussed. So entropy of an ideal gas, we have to start from the first mathematical form of the first law of thermodynamics, and instead of minus W we are using the term PdV. Suppose that only mechanical work is involved. So if only mechanical work PdV is involved and the heat change is reversible in nature, then the mathematical problem of the first law is dq equals to du plus PdV. So this is the equation. Now if both sides are divided by temperature T, then it gets the form dq by T equals to du by T plus PdV by T. Now we know that if this heat change is reversible in nature, it has been mentioned here, reversible in nature, then dq by T must be equal to the entropy change ds. And since the relationship between du and heat capacity is also known, so that du equals to ncb dt, then this value can also be put here by replacing du. So here instead of du we are writing here ncb dt by T, where n is the number of moles of the ideal gas, cb is the heat capacity at constant volume, and dt is the temperature change, infinitesimal temperature change. And from the ideal gas equation, instead of P by T we can also write nR by V, because PV equals to nRT, so P by T equals to nR by V. So we get this relationship. Now let's integrate the equation both sides without giving limits. Okay, so integration of ds, integration of ncb dt by T, integration of nR dv by V. So here the constant terms are taken out of the integration sign. So finally we can write here ncb integration of dt by T. Here n and r are constants, so let us take them out of the integration sign, resulting in nr integration dv by V. Okay, so what is the result of integration? Since this integration has no limit, so some integration constant s0 must have to be included. So s0 is the integration constant, and the result of integration is of the previous equation, means this equation. This would give you s. This would give what? ncb ln T, and this would give nr ln V plus some integration constant. So here is the result, s equals to ncb ln T plus nr ln V plus some integration constant s0. Okay, now we know that the difference of two types of heat capacities at constant pressure and constant volume is nothing but R, universal gas constant. And also from this relationship we can write Cv equals to Cp minus R. So here in place of Cv we can also replace this Cv by the value Cp minus R. Okay, and this way we are going to have the entropy of an ideal gas in terms of Cp instead of Cv. Equation 1 is the equation where entropy of an ideal gas has been expressed in terms of Cv, and this way you can get another relationship like equation 2. So how we reach there? Now it is just put Cp minus R in place of Cv. Okay, and this way here ncp ln T minus nr ln T. Now this one, what? This is some constant n, this is another constant r, so nr is some constant. Okay, so let us separate the logarithmic term. So this is nr ln nr. Now another two variables, T divided by P, so nr ln T, and for this divided by P minus nr ln P. So we are writing here nr ln T minus nr ln P, and plus the integration constant term. Since this is one constant and as this s0 is another constant, so these two can be merged, and this may also be denoted by another term s0 prime. Okay, this is yet another constant. So here ncp ln T, it is as usual. Here minus nr ln P, this is also as usual, but here nr ln nr and s0 prime are what? They are another constant, so they are written here as s0 prime. Okay, and on the other hand, two terms has been cancelled that I didn't mention. This is minus nr ln t and plus nr ln t. These two had been cancelled, so they are also not appearing in this equation number 2. Okay, so this way we are getting equation number 1, where entropy of an ideal gas has been expressed in terms of CV, and equation number 2, where entropy has been expressed in terms of Cp. Okay, now what happens for three conditions: isothermally, isobarically, or isochorically? Okay, if the entropy of the system is changed from S1, if system 1 is S1, that is state 1 is S1, where temperature is T1, pressure is P1, and volume is P1, and then the system is changing to state 2, where entropy is S2. Okay, so entropy is changing from S1 to S2. It means what? Now at state number 2, entropy is S2, temperature is T2, pressure is P2, and volume is P2. In that case, equation 1 and 2, equation 1 can be written as equation 1. That means in place of S you are writing S1. Okay, in place of T you are writing T1, in place of V you are writing V1. Then again you are putting the same values for state 2. Okay, in that case, instead of S you are writing S2, instead of temperature you are writing T2, and instead of volume you are writing V2, and then subtracting them with each other. That means the left hand side, subtraction of the left hand side is what? Now S2 minus S1, which is in turn equal to delta S. On the other hand, the subtraction in the right hand side gives the result Cv ln T2 minus Cv ln T1. That means Cv ln T2 by T1. Similarly, nr ln V2 minus nr ln V1, that gives the result nr ln V2 by V1. So this is equation number 3. Okay, so during solving the numerical problems, you have to use all these equations. 1, 2, 3, 4, 5, and 6 are also going to be obtained. And look here, for the entropy expression in terms of Cp, similarly we can get the expression of delta S like ncp ln T2 by T1 minus nr ln P2 by P1. Okay, similarly just you put the value T1, P1, S1, again you put the value S2, T2, P2, and then subtract them. Then you will get the value of delta S. Thus we are getting equation number 3 and 4. Thus the entropy change of an ideal gas isochorically may be obtained from equation 3. Yes, equation 3 is what? Here it is ncb ln T2 plus nr ln T2 by T1 and nr ln P2 by P1. Okay, equation number 3. This is the right hand side of equation number 3. So if the change undergoes isochoric process, that means the volume remains unchanged. In that case this term would vanish, because in that case V1 equals to V2, volume is not changing, so this would be ln1, that means 0. So that equation 3 can be reduced to ncb ln T2 by T1. Similarly, for isobaric case, that means if the pressure is remaining constant, then P1 becomes equal to P2 and this term would vanish. Similarly, in that case delta S would become ncp ln T2 by T1. So thus equation 3 and 4 can be converted to equation 5 and 6 for two conditions. This is isochoric and this is isobaric. Okay, isochorically delta SV, V is suffixed due to constant volume and P is suffixed for constant pressure. Isobaric change in entropy. And the result for isochoric change in entropy is ncb ln T2 by T1. On the other hand, for isobaric change in entropy, and delta S P must be equal to ncp ln T2 by T1. So just difference in the value of Cp and Cv. Okay, here ncp ln T2 by T1, here in Cv ln T2 by T1, and here in Cp ln T2 by T1. Thus we are getting equation 5 and 6. And if the change is isothermal, then what? Look here again. Here T1 equals to T2 for isothermal change, so this term would vanish, or conversely this term would also vanish. So we are going to get two expressions in terms of volume. Here nr ln V2 by V1, and here also minus nr ln P2 by P1. Both can be applied in case of isothermal changes. Okay, so according to the availability of your data, if you have the volume change data, then apply equation number 7, and you have the pressure change data, then apply equation number 8. And this equation number 8 has been rearranged as delta T ST, that means isothermal entropy change. This negative sign has been eliminated by just changing the numerator and denominator here. So this rational relationship has been reciprocated here, so it gives instead of P2 by P1 we are writing here P1 by P2. Okay, so equation 7 and 8 is the isothermal entropy change. Now move on to the numerical problems on entropy. Okay, problem number 1, you have to calculate the entropy change when 10 gram of neon is heated from 27 degrees Celsius to 227 degrees Celsius at constant volume. Okay, so you have the ideal gas and you need to calculate the entropy change. So the data here is the T1 and T2 data is given, and the V1 and V2 are same. So you know which equation has to be used. Before that, let's collect the data from the problem. First of all, what is the number of mole? We know the molecular weight of neon is 20 gram per mole. So it is for 10 gram, it should be 10 by 20. That means half mole. Okay. And since this is a monatomic gas, so its heat capacity at constant volume must be equal to 3 calorie. This is a known thing. So you will not be provided with this value. Okay. You have to use this value from as if you know this. Okay. And the examiner would want you to know this value. So this value would not be provided. You have to bring this value from your knowledge. Okay, fine. Now the temperature 227 degrees Celsius T2 plus 273 equals to 500 Kelvin, and T1 227 plus 273 equals to 300 Kelvin. Okay, so let's just apply this equation. Delta is V. Okay, this NCBL and T2 by T1. So put the corresponding values. Instead of N half mole 0.5, instead of CB 3 calorie per Kelvin per mole, and here ln 500 by 300. So the unit must be calorie per Kelvin here, not per mole, because this is for half mole. So if it would have been 1 mole, then you could have put the value per mole, but here for half mole, so the entropy change is 0.76 calorie per Kelvin only. Okay, so that's all about the problem number 1. Now problem number 2. One thing I must say during this numerical problem solution, that when the problem is given, you pause the video and try to do it yourself. Okay, then you tally your answer with the discussion which are going on here. Okay, fine. So what would be the change in entropy when 10 gram of tin is heated from 293 to 573 Kelvin? The melting point of tin is 500 Kelvin. It has latent heat of fusion 14 gram calorie per gram. Specific heat when in solid form, it is 0.055 calorie per gram, and when it is in the liquid state, then it has the specific heat 0.064 calorie per gram. Okay, so you have to calculate 3 entropy changes separately, and afterward just add them, so that in order to get the overall entropy change. First of all, solid tin to its melting state. Then the melting is a process. Okay, step 2. And in the third step, melting molten tin to the molten tin to higher temperature. That means solid tin from 293 Kelvin to 505 Kelvin up to the melting point. Then melting process until it completely melts. This is the second step. And then the molten tin, that means the liquid tin, from 500 Kelvin to 573 Kelvin. That's the step 3. So during this process, the specific heat of solid tin can be used, and during this process, specific heat of the liquid can be used. On the other hand, in between the first and third step, in between the latent heat, that is 14 calorie per gram, this data can be used. Okay, so this is the map, and during this process, the entropy change delta is 1. During the second process, entropy change delta is 2, and during the third process, entropy change is delta is 3. So the value of delta is 1. This is integration T1 to T2 to dq by T. Okay, T1 is 293, T2 is 505, and dq is nothing but the mass into specific heat into dt. Okay, so it is ms dt by T, and mass is given. First of all, we have done the integration here. Ms is the constant, so ms, then integration of dt by T from the limit 293 to 505, resulting in ln 505 by 293. Okay, now put the value. The mass of tin is 10 gram. Specific heat of tin at when it is in solid state, it is 0.55 calorie per gram, and then ln 505 by 293, and the result is 0.299 calorie per Kelvin. Now the delta S2 value is simply calculated by dividing the heat change with the melting temperature. For 1 mole, for 1 gram, the latent heat of fusion is L. So for m gram, it is m into L. So here the values are, instead of m, we are putting 10 gram, and 14 calorie per mole is for latent heat of fusion of solid tin into liquid tin. Okay, and divided by its melting temperature 505 Kelvin. So the result is 0.28 calorie per Kelvin, delta S2. And finally, the value of delta S3. The value of delta S3 is similarly as we have done in calculating delta S1. It is integration from T1 to T2. We are writing T2 to T3. Okay, and same way dq by t, the same way ms dt by t. Here also ms ln T3 by T2. Okay, T3 is 573 and T2 is 505. And here in place of S, instead of 0.55, we are writing here 0.064 calorie per gram. Okay, the specific heat for liquid tin is something else. Okay, it was 0.55 for solid tin, but for liquid tin this value is something greater, and this is 0.064. So that is the difference. And here the values of T1 and T2 also have changed. It has become the value of T3 by T2. Okay, so the overall result is 0.08 calorie per Kelvin. So the overall entropy change is their summation, delta S1 plus delta S2 plus delta S3, and the result is 0.659 calorie per Kelvin. Okay, now move on to problem number 3. What would be the entropy change when 10 moles of an ideal gas be doubled by expanding against vacuum? So the volume is changed. Okay, V1 becomes 2V1. Okay, so in place of V2, you are writing here 2V1, and just put the just use the equation of delta ST in terms of V1 and V2. So we know that it is nR ln V2 by V1, and in place of V2 we are writing here 2V1, and N is 10 mole. The number of moles is given. R is the universal gas constant, and here 2 into 0.693. ln2 is 0.693. Okay, here some multiply sign is missing, so when you are taking the note from the screenshot, you must put this multiplying sign here. Okay, 10 into 2 into 0.693. so this is typing error. Anyway, the result is finally 13.86 calorie per Kelvin. So this is a very easy problem. Okay, now next, number 4. 1 mole of an ideal diatomic gas. So diatomic, it is given, diatomic. So you know the Cp and Cp values of diatomic gas. You know the Cp is what? 7 calorie per Kelvin per mole, and Cp is 5 calorie per Kelvin per mole. Okay, that is why this data is given here, diatomic gas. So it was initially at 25 degrees Celsius and 1 atmospheric pressure. Okay, the gas was transferred to the state when temperature was 100 degrees Celsius and pressure 10 atmosphere. So both temperature and pressure are changing, so you have to use the equation in terms of temperature and pressure change. That means delta S equals to NCP ln T2 by T1 minus nR ln P2 by P1. Okay, that equation. So you have to calculate the entropy change. So in order to do this, we are just fetching this value, okay, from the literature. Cp equals to 7 calorie per Kelvin per mole for a diatomic gas, and the equation which is applicable when temperature and pressure are changing. So it is NCP ln T2 by T1 minus nR ln P2 by P1. Okay, and the result is here N is 1 mole, Cp is 7 calorie, and ln T2 by T1 373 by 298, and here N is 1 mole, R is 2 calorie per Kelvin per mole, and ln P2 is 10 atmosphere, P1 is 1 atmosphere, so it is ln 10 by 1. Okay, and the final calculation gives the result minus 3.034 calorie per Kelvin per mole. So entropy is decreasing here. So one more conclusion you can draw from here, that on increasing the pressure of a system, the entropy decreases. Although temperature is increasing, but here the entropy is also increasing, but this increasing effect has been overcome by the decreasing effect of pressure change. Decreasing effect has more impact on this system. So finally the negative entropy change has been obtained. Okay. But you keep in your mind that when temperature is increasing, entropy is increasing, but when pressure is increasing, entropy is decreasing.